Exponential functions are functions that have this form. F of x equals b to the x. The b is a constant number, and it is called the base. There are some requirements on b. b may not be negative. It has to be greater than 0, and it may not be 1 either. So requirement or requirements, depending on how you count them, is that b has to be between 0 and 1, or b has to be bigger than 1. Of course, not both, but one or the other. Um, so b cannot be 1. If we have that b is equal to 1, then we don't have a true exponential function. If b is negative, then that is not an exponential function either. So b is 1, or b is between 0 and 1. And we have two cases. I'm going to label this as case 1 because that is the most typically, the one we most typically see. So I'm going to label that as case 1. But that's just me labeling it as case 1. It's not like everybody labels that as case 1, and this is case 2. We most of the time talk about case 1, but a lot of the things except for about 1 does not apply. Anyway, let's start with this one. So one of the most typical examples of an exponential function is when b, the base, is equal to 2. So let's label that as an example. So if f of x equals 2 to the x, not just 2, but 2 to the x, make sure you know what this looks like. If this is the input and this is the output, even though it doesn't say that this is equal to y, we assume that y is the output, which is the same thing as f. So when x is 0, 2 to the 0 is going to give us 1. 2 to the 1 is going to give us 2. To the 2 is going to give us 4. 2 to the 3 is going to be 8. So every time we move up by 1 unit, the output will double from 1 to 2, from 2 to 4, from 4 to 8, from 8 to 16. I'm going to continue the table down here because I'm running out of space over there. So 4, 5 is going to go to 32, 6, 64, 7, 128, 8, 256, and then you can continue doing this on and on, doubling and doubling and doubling. And that increase is very quick. At first, it may not seem very quick, but it does go up very, very eventually. Once you get to a fairly big number, such as in the 200s, then doubling that makes the output increase by a huge amount. Then you got 512 and then 1,000. By the time we get to 10, we're already in the 1,000, and then 2,000, 4,000 and change. So very, very quickly we get to a million. I mean, if it takes 1 through 10 to get to 1,000, another 10 gets us to 1,000,000. Think about that. So by the time we get to 20, we get to 1,000,000. And by the way, make sure you know how to plug this into calculators. I don't think you have to buy a calculator such as this one. This calculator will not do exponentials very well because, well, it doesn't have an exponential key. This one does. There's a couple ways to do this. Let me clear that up. So if you have 2, and then you put this caret, some people call it a caret, and then 20 gives us a very, very large number in the million range. And then if you put another 10, then all of a sudden we are in the, well, what is 1,000 million? That would be 1,000,000,000. And so every 10 takes us to another level, so 2 to the 30 all of a sudden puts us in the billions, and 2 to the 40 in the trillions, and those numbers are just huge. On the other side of the spectrum, if you put -1, we end up with a half, because 2 to the -1 is the same thing as the reciprocal. -2 puts us at 1/4. -3 puts us at 1/8. And again, those numbers don't seem to be going down very quickly, but they do. There's a lot of difference between, oh, I made a mistake here. I didn't mean -1/8. All the outputs have to be positive when we have an exponential function. So we go to 1/8, and then we're going to go to 1/16. And very quickly, we get to the 1/1000, which is 0.001. And that is a very, very tiny number. And then if we go to the -20, we're going to be in the 1/1,000,000. It's actually a little close to that, even smaller than 1/1,000,000, which is 0.000001. And that's very, 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 very tiny, very small. So on one side of the spectrum, by the time you get to 20, you get to the million, which is huge compared to 1. And on the other side of the spectrum, if you go to -20, you are at 1/1,000,000th. So it is very interesting, because if we look at the sketch of the graph doesn't, I mean, it shows what's going on, but to a point. So this is kind of how it goes. For sure, it will go through 0, 1. And then we will have a point that is going to be 1, 2. Remember, when we're still working on this example, 1, 2. And another point on the left will be -1, 1/2. So if you did not know where the graph comes from, this kind of gives it away. The 1, 2, especially because of the 1, 2, tells us that this is 2 to the x. Had this been 1, 3, then we would have 3 to the x, and so forth. But if somebody gives you 3, 8, then you got to think, hey, well, wait a minute, 3, make sure this is a 1, because if had it been 3, then we would have, 2, 4, 8, then we would still have 2. Anyway, so this graph is not it does kind of work initially, because yeah, it goes down to about half, but then very quickly we go down to another half, and then we're at 1/8 and 1/16 and 1/32, which is super tiny, but then 1/64 is even smaller. Very quickly we get to the point where the thickness of the pen is not thin enough to actually differentiate between the graph and the x-axis. Notice that I drew the x-axis as a dotted line, because we actually have an asymptote. The graph will get closer and closer to this dotted line, which is y equals 0. Yes, y equals 0 is the horizontal line on the x-axis, and that is the asymptote. Now, some of us think, oh, the asymptote always has to go down, the graph has to go down to the asymptote in both sides of the graph. And the answer is, if we had a rational function, that would be correct. But this is not a rational function. It is a completely different kind of animal. So that's why we differentiate this from the previous video, which was about rational functions. These are not rational functions. There's no rational function, no polynomial that will create this kind of behavior when we compare the inputs and the outputs. That's why we have a whole video about exponential functions, because they are just different, and they are necessary also. They're more complicated in a way, and another way they're simpler. There is only one asymptote, for instance, that makes them simple. Yeah, they're complicated in the sense that they grow very quickly. They're complicated in the sense that they are very difficult to solve. Not like polynomials were not difficult, but at least we kind of have an idea of how to solve them. They're just different, and we have to study them differently. So these are exponential functions. This is actually one example of an exponential function. And again, once we get to here, we're going to get to 4, which is not too far up. You know, if this is a 2, which kind of makes sense, 1, 2, 4. And then we get to 8. And then we get to 16. And then we keep going. I mean, before you know it, I'm in downtown, you know, we are in Plainfield, the town, because that's north. That way is north where I'm sitting here. So if you keep going up very quickly, we get to Rockford, and then, well, Cadillac is a little bit to the left, so maybe, you know, it just keeps going to the right. I mean, a little bit to the right, but not a lot. But it goes up very, very quickly. Remember, by the time we get to 20, so this is 1, 2, 20 is not that big of a distance. We're already like at 1,000,000, which is a huge distance going north that way. Yeah. Oh, I just realized this is north. Yeah, that's north, and then that is to the left is west, and to my right is east, and of course behind me is south. That just happens to work out in this desk where the way I'm sitting down. Um, yeah. So become familiar with this function. As a second example, if you have f of x equals 3 to the x, we're going to have the same horizontal asymptote, and the asymptote only affects the left side of the graph. It does not affect the right side of the graph, which is not what happens with rational functions. So again, we have a horizontal asymptote, y equals 0. The graph again goes through a 0, 1. That is always the y-intercept with, I call those pure, and there's going to be a reason why in this video. I call them pure exponential function. Yep, and this goes up. Technically speaking, in comparing this graph with this graph, this one should have been a little more bent, because this one actually goes up faster. See, the point corresponding to 1 should be 1 comma 3 as opposed to 1 comma 2. So this point should have been even higher. We're drawing a sketch. So as long as we don't put them on the same graph, it's sort of okay to not have them proportionally correct. So this point on the left would be negative 1 comma 1/3, which really, this goes down very quickly. Imagine from 1, this is not to scale, of course, because 1/3 would be even lower. And then we go to 1/9. I mean, if we thought this graph went quickly, you know, to big numbers such as 1,000, you know, by the time we get to 10, we get to over 1,000. This one is going to go even faster. Actually, now I'm curious about this. Let's put the x's and the outputs. You know, of course, 0 gives us 1. 3 to the 0 will be 1. 1 gives us 3 to 9. It looks very innocent. 327, 481, 5, 343, 6, 729, if I'm not mistaken. So that is close to 1,000. And then by the time we get to 7, 3 times 9 is 27. We carry 2. 3 times 2 is 6, 7, 8. 3 times 7 is 21. Yep, we get to 2,187 just by the time we get to 7. In the previous exponential function, 2 to the x, we got to 1,000 by the time we got to 10. You know, that was 256, double that, 512, double that, 1,024 by the time we get to 10. Here, at 7, we already double what this function got to 10. So this is even faster. Imagine that. It just grows and grows very, very quickly. You know, that's why they say, when people say, you know, this grew exponentially, that's what they mean. It just, I mean, initially, hey, it doesn't look too bad, but eventually it gets to be huge, huge. I mean, you get to Rockford much sooner, and then you get to Canada even sooner, Canada North, because you could go east rather Yeah, I'm getting confused. Yeah, east, you can go east and get to Canada also, but where we are, but we get to Canada very, very quickly with this. And then if you use 4 to the x, that's even sooner. 5 to the x. I mean, where do you stop? 10 to the x, 10 to the x. Oh yeah, let's do 10 to the x. Before I do that, I want to compare the two in one graph. So we have an asymptote. We have 2 to the x, and 3 to the x will have to go. Let me do it in a new page because I don't want to. So I don't want to squeeze it too. So there's the asymptote y equals 0 for both of them. The y-axis, we have 2 to the x. And now because I want to compare correctly, 3 to the x is under, then they both cross at 0, 1, and then 3 to the x goes up higher. So that is very interesting. 0, 1 is common to the two functions. We're comparing 2 to the x with 3 to the x. And of course, 3 to the x is going to go higher, and 4 to the x would be higher. And if you have 1.5 to the x, that would be lower than 2 to the x. And 1.1 to the x would be even lower, but they're still going up. They still have the same shape. All of them have the same horizontal asymptote. All of them go through 0, 1. It just happens that one goes down faster in the same way as it goes up faster than the other one. So they cross here, and one beats the other. So this one will beat 2 to the x for sure. It will beat 2 to the x. 3 to the x beats 2 to the x going up faster, and it also beats 2 to the x going closer to the asymptote. It gets closer to the asymptote faster. Wow. And then 4 to the x and so forth. So 10 to the x, oh, that's the one I was getting excited over because, I mean, if we think 2 and 3 to the x are fast, hey, 10 to the x, boy, 10 to the x is, let's just make a quick table, 0, oh, let's put the x's and the y's here. So 0 goes with 1, 1 goes with 10. Ignore that line. Well, let's put more lines, I suppose. 2 goes with 100. 3 goes with 1,000. I mean, we thought 3 to the x was fast. Watch, 2,000. By the time we get to 3, boom, we're at 1,000. 4, 10,000. So by the time we get to 4, we already exceeded the 2,000 that this function. So see, all is a matter of proportion. So we're being, it's all, who's the fastest one? Well, that's all relative. You think you're fast, 3 to the x? Well, I'm going to bring 10 to the x. 10 to the x is way faster. And then 5, I mean, well, that's 10 to the 5, which is, I have to think about that. Oh, 100,000. And then 6 is a million. So I'm not even going to write that with zeros. It's 1 million. And by the time we get to 9, so let me continue the table here. 9, that's going to be a billion. And then 12, we get a trillion. And then 3 more, that would be 15. That's a quadrillion. I mean, remember when I was telling you north is that way? So Rockford, we're in Grand Rapids, Michigan, then you go to Rockford and that way, because you go a little bit to the right, and then pretty soon you're into Canada. Well, with this function, pretty soon you go all the way around the earth and come back to Grand Rapids because it's just so far out. I mean, if we were continue on earth, or I guess if you go off earth, on a tangent and you go in space, I don't know where you would end up. But so the point I'm making is, this 15 is not even that far to the right. I mean, this is what? This is 5, so 15 is about 3 times as much, not bigger than the width of this desk. But boy, this number is gigantic, huge. I don't even want to. And then the other way, if you go to -1, then those numbers get tiny, tiny, super tiny. I mean, for all practical purposes, the pixels start getting one on top of the other as far as comparing the asymptote and the exponential function. Yeah, yeah. And then somebody may be thinking, well, 10 to the x is the best one, the fastest one. Well, it doesn't end. You can do 100 to the x, and that would beat this guy. And then you can have 1,000. I mean, it doesn't end. On the other end of the spectrum, you could have 1.1, 1.01 to the x, 1.001 to the x, and they're getting a little more flat, but still they are exponential. They still grow a lot. So those are exponential functions. Get a feel for them. They're very important. Um, let's do another example. So all of these examples, the three examples we showed this far, are case one when the base is bigger than 1. 2, 3, 10. When the base is smaller than 1, between 0 and 1, then the graph kind of changes radically. So let's do example 4. What about f of x equals a half to the x? So this number, the base, is a half, which is between 0 and 1. And consequently, the graph is going to be looking like this. It's going to go down instead of going up. I guess it depends how you see it. It is going down. We read graphs from left to right. And consequently, as we read this graph from left to right, the graph is going down. The point we intersect is 0, 1 still. And the point here on the right would be 1 comma a half, because a half to the 1 is a half. And then 2 corresponds to 1/2 squared, which would be a quarter, and so forth. But on the left, then we end up with -1 and 2, and then -2, 4, -2, 8, rather, -3, 8, -4, 16, -5, 32. Do those numbers look familiar? Well, yeah, they're here. 2, 4, 8, 16, 32, 64. So we will end up with those numbers just on the other side of the y-axis. In fact, there's a relationship, a strong relationship between this graph and that graph. Can you tell what the relationship is? One is the flip of the other. If you turn this graph this way, then you end up with this. And if you turn this one the other way, then they're a flip of each other. I mean, a turn across the y-axis. Yeah. And that is not a coincidence. It is a fact. That is what happens, because this can be thought of as 2 to the negative x. So if you compare 2 to the negative x with 2 to the x, we are replacing the x with negative x. And if you remember our video about transformations, what that means is that we are turning the graph over the y-axis. Yeah, we're reflecting. Reflecting is the correct word to use. The graph over the y-axis. So 2 to the x, 1/2 to the x, they're very much the same, except that, again, one is a reflection of the other. So we have the same asymptote. Y equals 0 is the horizontal asymptote. The graph keeps going closer and closer to y equals 0 without ever touching it. In this case, we still go through 0, 1 as all the previous examples. And if you go from right to left, the graph increases very, very rapidly. There is many applications of exponential functions, whether they are case 1 or case 2. There are many applications. I don't think I have to show in this video an example where we have f of x equals 1/3 to the x. You would go just lower. Well, it will start out higher on the left, cross through 0, 1, and then go lower. And then 4 to the x, rather 1/4 to the x, or 1/10 to the x. That would be pretty steep, and then come down through 0, 1, and then go lower very quickly again. Yeah, so those are exponential functions. We have to know some of their properties. So let me draw a case 1 function and then look at some of the properties. So first of all, the domain is everything. We may plug in any number we ever want, 0, 1, 2, 3, and all the numbers in between, and all the numbers beyond 3, -1, -2, -3, all the numbers in between, all the numbers to the left. There's no number we have to avoid. So the domain of any pure, I call them pure. I'll tell you why in a moment, but a pure exponential function goes from -infinity to infinity. There's no thing you have to exclude. All the numbers are included. The range, okay, that's very important. If the range goes from 0 to infinity, remember the range is the set of outputs that we may have. 0 is the lowest. This graph will never go under the x-axis. Never, ever, ever, unless we transform it. So keep that in mind. And that's why I'm calling it a pure exponential function. A pure exponential function has this kind of equation, either y or f of x equals b to the x. That's it. Nothing. This number could be a weird number, such as 1.2, or, well, then again, weird is relative. What is weird to one person is not to the other. So, but some kind of not simple number, like a simple number is like a 2, a 3, a 5. That's a simple number. But a weird number would be like square root of 7 to the x, and that wouldn't even be that bad actually. um you know it's just, or some fraction, like 2 plus the square root of 5 over all of that over, I don't know, uh 3. That would be more weird, but anyway. The point is, it doesn't matter what number that is, as long as the only thing we need to know is it bigger than 1, is it smaller than 1, and whether it's positive or not. And yeah, anyway, the range goes from 0 to infinity. Notice that we don't put a bracket here. There is no square bracket. We keep it open because we have the kind of asymptote we have here, which is y equals 0, is the one where the graph gets closer and closer without ever touching it. There are some asymptotes that we do cross. We saw that in the rational function video. But in this, and there are many asymptotes that we never ever cross. This is one of those. But that doesn't mean we never ever cross any asymptote. Sometimes we do, sometimes we don't. This is one of those cases where we get closer and closer only on one side of the equation, but we never cross it. So that is the range. There is no symmetry. No symmetry. Let's write it down. No symmetry. In other words, not odd, not even, because it grows on one end and it goes down on the other end. So there's no way we can have some kind of symmetry. And it definitely, there is no symmetry over the origin because there's no negative portion to this. There are other properties. Oh, one thing before I forget that I could ask you in a multiple choice question is whether the range starts with 0, including 0, or excluding 0. And here I'm telling you, well, it cannot include 0. We have to have more than 0. So this interval has to be open. All of those, well, the asymptote is always y equals 0. Asymptote is always horizontal, y equal to 0. Okay, so we got the domain, the range. I'm going to put a bullet. No symmetry. We got a horizontal asymptote, and it's always that it goes through, the graph goes through 0, 1 always. It also goes through 1b. So in general, if we don't know what the base is and we just generically call it b for base, then we will go through 1b and -1 comma 1 over b. Now mind, If b is a small fraction, such as a half, then the reciprocal is 2. Yeah. So if b is small, 1 over b is big. If b is small, oh, I just said that. If b is big, then 1 over b is small. So they flip flop. Okay. Um, let's look at some applications. Yeah. Before we go into the applications, let's talk about interest. Charging interest or paying interest for money. Okay, so interest, as in money. Okay, so let's look at an application. Um, so dollar symbol interest. Okay, and we're going to start with a simple interest. So there's many kinds of interest. There is simple interest, there's compound interest, and there is continuously compound interest. So again, there are three. I guess I should write them down. Simple, compound, and continuously compound. Compound interest. So there are three of them. Simple, compound, and I'm very likely going to be asking you questions about problems of those three. So we really want to pay attention to those. 1, 2, 3, 4. I'm counting the examples. So the next example will be example 5. Okay. So let's say you borrow money from a relative. Let's keep things simple. You borrow $1,000 from a relative, and the relative is going to charge 2% per year, 2% per year. Okay. And you're going to pay back in, I don't know, you're going to go to college or something, and you're going to pay back in 5 years. To pay back in 5 years. Okay. At simple interest. Simple. This has to be stated at one point or another. Whenever you make a contract, and we're assuming this is a contract, that is a very important part of your contract. Is it going to be simple, compound? And if it is compound, which way it is going to be compound? So that's why we are going through these examples to show the difference. Now, if we don't put the period of time, typically it is understood that it is per year. So no interest, no period of time means usually per year. That's another thing you want to, if whenever you draw a contract, you want to know what period of time, you want to know your interest, the amount, and how long you're going to have the the interest. Also, we're not going to go that deep in this problem, but when you're drawing a contract, you want to know whether if you pay early, let's say you win the lottery and you want to pay your debt early, well, do you have to pay it with full interest, or can you pay just the interest accumulated up to when you won the lottery? Those are two different things. There's a lot of things you want to clarify before you sign a contract. Now, this is a relative, so it's just an oral contract, but still, let's go through this. So simple interest means this. You know what? I'm going to change the 2% because as we go through this problem, we want to dramatize the difference a little bit, and 2% may not do it. Let's say 10%. Okay. Borrow at 10% per year. Sorry to change that on you, but we haven't even started the problem, so it's a little fair, Okay, so how much is 10% of $1,000? doesn't take too much to figure that out. It's $100. So $100 per year. So year one, 100, year two, another 100, year three, another 100, year four, another 100, year five, my pen is falling off, another 100. So you end up with $500. So the question is, oh, I didn't ask a question. So how much do we pay back at the end of 5 years? Question mark. Well, again, 10% of $1,000 is $100. So we pay $100 each year, and that gives us a total, a grand total. We always ask for the grand total. So that is principal plus interest, and the grand total we have to pay back is $1,500. That's how much we have to pay back after 5 years under this contract. Okay. Okay. Example 6. Same, I was going to copy the whole thing, but I'm just going to say same as, oops, as 5, but compounding interest once per year. Okay. Okay, so this is the situation. Year number 0. So that's the moment you are taking the money from the lender. You get $1,000. You put them in your pocket. Okay. And then a year goes by. Pretend this is the situation with compounding interest. Somebody knocks on your door and says, I want my money back. And you say, wait a minute, we said 5 years. I don't have your money back. I don't have any money. And then the lender says, well, I'm going to assume you gave me the money right now. So I'm going to assume you gave me 1,100, and I'm going to lend it back to you right now. So you're at the door, and this imaginary transaction is happening. You are giving the $1,100 to the lender. The lender gives you right back the $1,100. That didn't happen, of course, but that's how we think of compound interest, because the lender says, you owe me $1,100. So at this moment, I'm pretending you are giving me the $1,100 and I'm giving it back to you. If I was going to cash right now, cash out, you would be giving me, the lender says, $1,100. So give them to me. Now I'm giving them back to you. Now we start a new loan, a new borrowing the money, but this time it is more money. Okay, another year goes by. And then the lender comes to your door and knocks on your door and says, I want my money. And you say, wait a minute, we said 5 years. Oh, okay, you don't have the money. You're right. By the way, how much do you owe me right now? And well, because the lender assumes that the new loan, the new borrowing is for $1,100, now the lender is going to charge 10% of the $1,100. So here the interest was $100. Now the interest is $110. So now we owe 1,210. Okay, another year goes by, 3, and the lender is going to charge 10%, not over the original $1,000, but over the $1,200 and $10 that now we owe after year number 2. So now the lender is going to charge $121. See how quickly the interest? Now, the funny thing to me, I mean, it is what it is. I'm not claiming that it is not what it is, but it is funny to me that the lender is charging interest, like here $10, for money that lender never really gave to the borrower. You know, in the imagination of the lender, yeah, they gave an extra $100, but you, as a borrower, you never see the extra $100. It's just in the imagination of the lender. Anyway, but this is the way it is. That's a credit card is actually worse than this because the interest is higher than that. It and actually it's worse because a credit card charges you interest once per month, not once per year. So it's even worse, double worse. Anyway, but this is the way it is. It's the so now how much do we have? Let's see, 331 4 years. Now we're gonna, is that right? Yeah. Now we're gonna add $133.10. So we go on 1 4 because of the 100. 33 and 31 is 64 and 10 cents. And then finally, during the last year, they're going to charge us $146.11. So I got to do the addition. Whoa, 146. So I know the decimals is going to be 21. 4 and 6 is 10. We carry 1. 6 and 4 is 10. And the one we carried is 11. We carry 1. 5, 6. Okay. So 1,610.21. Okay. In comparing back here, I just want to do a quick question. I'm going to carve a little bit of space here just to show you the difference. Year 0, in this scenario, you're given $1,000. They're going to charge after the first year 100. So now we have to pay 1,100. Second year, 1,200. Third year, 1,300. Fourth year, 1,400. Fifth year, 1,500. So simple means, as the name says it, we're just going to charge 10% of the original amount throughout the whole thing, throughout all of the 5 years, year after year, $100, $100, $100, $100. Compound means we are resetting the loan. Reset the loan at the first year, reset at the second year, reset. So we are adding the interest that we accumulated we're folding it into the loan itself. And that means we're going to pay even more interest because we're going to pay interest of the interest. So at this point, we're paying interest not only of the 1,000, but interest on this, interest on that, on the 200, interest on the 300, interest on the 400. So by the time we finish, let's see, that was 1,500. The difference between the two is 110 and 21 cents. That's how much we have to pay in difference if we pay simple versus compound. Simple versus compound. But it gets worse. If you actually do this with a bank, and you don't pay any of the principal, example 7. So same as, well, we got to do one step in between. Same as last examples, but compounding twice per year. So that is called biannually. Biannually. Yeah. So they compound the interest rate twice per year. It gets really complicated because instead of doing 5 cycles, starting with 0, we do 1 cycle, 2, 3, 4, 5. Now we got to do 10 cycles because the first half a year and then a full year, then 1.5 years and 2 years. So there's going to be In betweens, half, one and a half, two, two and a half, three, three and a half, four, four and a half, and finally 5. So this gets complicated. You know what? Before we get to this, because it's getting complicated, let's go back to example 6. So I'm going to go down here and say back to example 6 and see how we do this. Now, when you are charged 10% of anything, you know, like $1,000 and 10%, you figure out how much the 10% is and then add it on. But there's a shortcut to that. So instead of adding, I'm going to put a line here to distinguish example 7 from example 6. Instead of figuring out 10% and adding, we can do that in one computation. We can multiply $1,000 times 1 plus 0.1, or the same thing as 1,000 times 1.1. So the 1 corresponds to the principal and the 0.1 corresponds to 10%. That's how we figure this out. So again, instead of figuring out 10% of 1,000, which is $100, and then adding that to the $1,000, no, we can do that in one shot. 1,000 times 1.1 keeps the principal and adds on top of that 10%. By the way, you can do that with tax. In Michigan, the sales tax is 6%. So if you want to know how much you're going to pay tax included, all you have to do, okay, so this is just a side note, okay, 6% tax added to the price of something can be done just with one multiplication. Let's say you are buying something that is $52, and you want to know how much you are going to pay out the door with the tax. All you have to do is multiply by 1.06. 6 corresponding to 6%, 1 corresponding to the principal. And that's it. Where's my calculator? There it is. So if you have 52 times 1.06, there we have it. We have to pay in total $55.12, one computation. Now, if you want to do it in two computations, sure, figure out 6% of 52. So that is 0.06 times 52, or 52 times 0.06, same thing. So 312. So if you wanted to do it in how much you're going to pay, so, or you can do $52 plus 3.12 in tax, then you get to the same answer, 55.12. But if you want to skip this step of figuring out how much the tax is and then added that on to the principal or the original price, you can just do that in one shot. Well, that's what we're going to do here. In fact, I haven't finished. To go back to example 6. Let me carve more space here. Yeah. So again, continuing with example 6, remember that is the one where we compound once per year. So instead of doing figuring out how much we have to pay each time, you can do 1.1 5 times and still multiply by 1,000. Really, this is what's going on. Multiply 1,000 by 1.1. That's 1 year's worth of principal plus interest. Multiply by 1.1, that's 2 years. So whatever the answer is here, multiply it again by 1.1 and you get 2 years. Multiply by 1.1, 3 years. 4, well, good thing I'm using skinny numbers such as 1 because then they fit nicely. Well, not very nicely, but they fit. 1, so again, this is 1 year, 2, 3, 4, 5, except that instead of multiplying the 1,000 times 1.1, well, wait a minute, let's do it to make sure that it works. 1,000 times 1.1 times 1.1 times, that's 2 this far, 1.1 times, that's 3, 1.1 times, that's 4, 1.1 equals 1,610 and 51 cents. Is that what I got here? I better have that. 1,610 and 51. I must have added something wrong here because I got 21 instead of, where's my mistake? 30. So then we add 41 cents. Oh, I put 11. That should be 41 cents. And that brings us up to 51 cents. Is that the answer here? Yep, 51. Okay, so we're good. Yeah. Okay, so if we did that, actually, that was even better because now we fixed the mistake I made over there. Or the other way to do it with this little calculator is to say 1.1 times, so that in this kind of calculator, if you put equals, that multiplies it with 1.1. Every time you put equals, once you start the times, it multiplies it again. So that is 2, 3, 4, 5, and then multiply by, most little calculators like this work the same way. So don't think this is a special one. 1,000, which is the principal, and it gives us the same answer. All right, so let's go back to 7, semi-annually. Now in semi-annually, if we are being charged 10% per year, and we are compounding every 6 months, every half a year, that means that they're going to only charge us 5% for the first half of the year and 5% for the other half. So it's not like they are charging 10% for each half of the year, it's 10% per year, but then we got to split that into 2. So we're actually going to pay 1.05, 1 for the principal, 5% for each half a year. Now, in 5 years, how many half years do we have? Remember, we got half, half, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. We got 10 of those, 10 of those cycles. And then we multiply with 1,000, and there is going to be our answer. Okay, so I'm going to do 1.05 times 1.05 times 1.05 times 1.05 10 times. Okay, 1.05 times. So that is going to be 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're going to multiply by 1,000. We go up, but not too much higher. $1,628.89. 89 cents. We're going to round to the nearest cent. And a cent is 2 decimals. Since the next number is 4, we stay with 89. Even if we had 49, that is still 4 for the next digit. So we stay with 89 cents. So we're going to pay $1,628.89 versus, if we compound per year, 1,610 and 21 cents. So we're $18 and change off. I did not fix the 5 here. Okay. Example 8. Same, but compounding monthly. Okay. So that is 12 months. That is, okay, how many months are there in 5 years? Well, 60. So, and how much is the percentage per month? Well, we got 10%, which we're going to divide. If we divide it by 2, as in the previous example, that's how we got the 5%. But we're going to divide that by 12. And that's a little unfortunate because the number is not going to be, oh, I guess it is not too bad. Now, here we do want to use all the decimals. I think I did this wrong. Let's do it again. So 10% divide by 12, 80. Oh, that's less than 1%. Okay. So what we're going to do is 1.0 and then 8. No, another 0 because this is less than 1%. 1% is 0.01. Yeah, we got to be very careful with the decimals. 0.01 is 1%. We're going to go even lower than that, which means 0.008, and then as many threes as we can fit into our calculator. So I don't like using decimals, and we're not using infinite decimals. I'm not going 3 forever. Only as many decimals as the calculator fits. And you may say, wait a minute, we're doing pennies. No. That is true for the dollars, but these are not dollars, these are percentages. So we put as many threes as we can fit into the calculator. And then we raise this to the 60th power because there's 60 months in 5 years. There are 10 half years in 5 years, and there are 5 years in 5 years. I know that's silly. So here we have 60. So what I should do, oh, and then we're going to multiply with 1,000. What I should do is 1.0083333. That's as many threes as I can put in that calculator. And I got to do this times, if every time I put equals, we're going to multiply by that number again. So I have to do that. Well, that's 2. And then all the way up to 60. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. You know what? Once you get to 30, you can multiply it by itself, and that's going to give us 60. That's a rule of exponents. Okay, let's do that. So I'm going to take this number. I'm going to put it into the memory. Just m plus means put it into the memory. Okay, I'm going to start with that number. I just didn't want to mess that up. I think I didn't have to do that, but let's just do that. Okay, times equals. There you go. So to the 60 means 1 point and this number. Yeah. Multiply by 1,000, and that's going to give us $1,645.30. Okay. By the way, there are many ways to get to an exponent of 60. Let me clear the memory. Okay. And let's start again with 1.0083333. You know, you can just go to, I don't know, to 5 times 1, rather that's 2, 3, 4, 5. And then you can multiply that. So that was 5 by 12 of those. So times, and then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's going to give us the same number. So there's many ways to do this. You can multiply this by itself just once, so two of those factors, and then do it 30 times. There's many different combinations, and you will always end up with the same answer. Or you can use a big calculator, or and I don't think you have to buy a calculator, because a lot of computers have a calculator built into the computer, or even the phone probably. I haven't checked mine, but I'm pretty sure there is something that you can use. So I wouldn't, especially if you're working at home, you don't have to, doing studying at home, you don't have to go and buy a calculator like this necessarily. Um, so so we do 1.008, and then I know this calculator only carries about 10. Even if I put, because you can put as many threes as you want, but don't do that in this calculator, because I don't know how many. It doesn't matter, because if you press enter, it's gonna chop this to as many threes as it can do it. So just do as 10 or so. All right, but then you can raise that with this caret exponent to how many do we need? 60. There we go. And then we can multiply by 1,000, which is our original amount we have to use, or our principal. And let me see this more closely. Same quantity. So we end up with the same quantity. Okay. What is the difference between those two? Let's see. Maybe $1 off from the 30, so about $16 difference. What about daily? 9. Daily. If we were to do the same thing, but daily, now that brings up a complication. We have to figure out the percentage per day. So remember, it was 10%, but that is per year. So then we divide 10 by 365. 10 divide by 365, and that's going to give us, now this is less than 1%. This is a percent, well, this is super small. As a percentage, now remember, this is 10%. So as a decimal, this is really 0.00, that takes care of the first part, and then 0 to 73972. Okay, so that's a tiny number. How many days are there in 5 years? Well, let's see. 5 times 365 days, and that excludes, of course, leap years or leap days, and that's okay. For purposes of this example, let's skip that. So there is 1,825 days in 5 years. Okay, so let's compute this. The formula, and by the way, I did not write down the formula on purpose. I sort of refuse to do that, not because you can look it up in any book. There's tons of places where you can find it. So I'm not telling you not to use it, but try to use common sense, please. How many cycles are they gonna use to reset the loan? Remember, compounding means reset the cycle, reset the loan. Every year, reset it, add the interest, and reset pretend you have a new borrowing of money. That's what's going on. So if we compound daily, that means that every day we're resetting the loan. And we're going to charge one for the original $1,000 and a tiny, tiny decimal, because 10% is going to be split up into 365 days. So each day we're going to charge a fraction of 1%. 1% would be 0.1. So this is a fraction of that, 3,972. But we're going to have 1,825 cycles. Now, even with all the math I know, I can probably, if push came to shove, I can probably figure this out, but we're going to use this bigger calculator. Again, especially if you are doing this, I want to just to clear, there we go. At home, you probably have a phone or a computer or a tablet or something, and those typically have a way to get exponents, that big of an exponent. So I'm going to put 1 point, I'm going to type in 1.00273,972, and we're going to raise that to 1,825, 1,825, enter. Well, what did I do wrong? Let me go back. Well, let's just clear. I'm going to clear again. So I don't know what I did wrong. 1.123 3972. Where's the exponent key? There it is. And then 1,825, 1,825. Yeah, we get a, a number multiplied by 1,000 times 1,000. And let me just double check something. 1648.61. 1648.61 cents. That's if we compound daily, every day, compared to monthly. Monthly, we have to pay 1,645 versus 48. The difference is very tiny. Notice that. The more you compound, the more money you earn or you have to pay, depends on which side of the borrowing and lending you are. But it doesn't, the farther you go, the less it increases. If you do this every hour, is it going to go up? Yes, but very, very, very little. Or every minute or every second. Is it going to go up? Yes. But at some point, it's not going to make too much of a difference. If it makes a difference of 1 or 2 pennies, that's probably going to be it at one point or another. In fact, you have to wait 5 years from monthly to daily to earn about 3 more bucks on $1,000. The banks are not going to do that. That is too much work, because then you have to start thinking, okay, did the person deposit the money in the morning or in the afternoon? It's just too much of a mess. That's why banks, I don't think most of banks won't charge interest. Well, I shouldn't say that. I don't know actually. But if I was a bank, I wouldn't. I would just probably do monthly, because the work involved in the computations is that much harder. And so might just as well just figure this out monthly. And if I really wanted more money if I was lending money, a lender, and I wanted more money, I'll just raise the interest rate. Instead of 10%, I will go for 12%. And that will give me more money than increasing the compounding. Having said that, we can compound every instant. Every single instant we can compound. And so there's a limit of how often we can compound, and we can compound instantaneously. Not once per second, not twice per second, not 10 times per second, but as many instants there are per second, which has an infinite number of instants. That's kind of weird to think about, but you can do that. So we get to continuous compounding. And it isn't like people are going to compute interest rate with continuous compounding. I have never seen that. However, mathematically, it makes sense to compound continuously, because then we don't have to think of days or minutes or hours, or not too much. It makes having continuous functions makes a lot of the math way easier. We have to pay a price though, because not everything we do is continuous. Even with money, we don't have continuous amounts of money. You have to break money down to pennies. However, the math that we apply with continuity is way, way simpler. And that's why many times we do that. We use continuous, and the price we have to pay is so tiny. I mean, down to pennies. We pay the price, and we say, fine, let's do mathematics with continuous functions, and that makes things way simpler and easier. So for continuous compound interest, we use a special name. So not a special name, a special number. Special number. It turns out that when we use something a lot, then we give it a name. So if I use this to, you know, white out things, I give it a name, we call it an eraser. If I use this a lot to perform computations, then we give it a name, a calculator. So whatever you use a lot, you give a name to it. Um, if you don't use something a lot, even if it had a name, we start forgetting the name. I forget things that I don't use frequently. I cannot think of one right now, but precisely because it's not in the top of my mind. Yeah, I'm not thinking of it. Um, but things that, oh yeah, people, like people I don't see, I saw maybe once every 10 years. I'm like, oh, what is the name of that person? I mean, that person obviously has a name, but I don't remember it because I use the name very infrequently. And the same thing happens in society in general. When we use something very frequently, we give it a name, and we keep the name, and we remember the name. And when something is not used frequently, then we forget. Like a quadrillion, that is after trillion, we have million, billion, trillion, and then quadrillion. I don't know if people know that, or quintillion, I guess, is the next one. Um, if you ask randomly a person, hey, what is 1,000 times a million? Well, that's not too bad. So a lot of people should say a billion, but then 1,000 times that, a trillion, and then after that they may not know the word because they don't use it frequently. Anyway, so there's a special name, a special number that we use very frequently, and it's so common. It's even here on the calculator. It's this number. And there's more decimals to that. Those are just the numbers, the decimals that are on the calculator. And we give it a name. It is the number E. And it is about 2.72. It is not 2.72. It is about, because there's many more there. I'm rounding it to 2.72. So that is the number that is used when we compound continuously. Okay, so so the formula we use is the following. So the principal plus the interest, if we compound continuously for 5 years at 10%, is E, well, 1,000, E 10%. Okay, so 10% is 0.1 or 10, either way, and then 5 years. So the interest per year, the number of years. And the beauty of this, see, this is way simpler than doing, what was it? Oh yeah, that to a big, I mean, this is almost, it gets to a point where this is, how do you control this? I mean, this is getting a little bit messy. This one, on the other hand, is so much neater and cleaner. And in fact, we can simplify this because 5 times 0.1 is 0.5. So 1,000 e to the 0.5 gives us the absolute maximum we can charge if we lend money at $1,000 at 10% for 5 years, compounding. It doesn't matter what compounding we do, the absolute maximum will be, okay, let's turn this on, 1,000 e with the exponent of 0.5. So that is the most that we can charge, 1648.72. 1648.72. Yeah. Which is only pennies, 11 cents, 11 pennies, 11 of those. Yep. That we can charge at the most, no matter how much compounding we do. As long as we stay with 10% and 5 years, that is the most we can charge. Yep. Yep. There are a couple other things I need to speak about. So this is the interest. There is one property I neglected to mention. Yeah, one more property about exponential functions. And that is, they are one-to-one. They are invertible. So all exponential functions are invertible. They are invertible. So there is an inverse to them. We're going to talk about the inverse of the exponential function in a different video. I can tell you now that it's the logarithmical function, the one that we're going to see. That's the inverse, but don't tell anybody. That's for the next video. Right now we're focusing on the exponential function. So the logarithmical, I mean, if you needed to know, now you know that the logarithms are the inverse of the exponential functions. But so that is another property. And the other thing I neglected to mention is the transformations. Well, it's not that I neglected it, it's just I have to do one thing at a time. But the next thing we want to talk about is transformations. And I'm not going to spend way too much time on this. I'm just going to explain a couple examples. Transformating exponential functions. So let's do some examples. Example 11. Let's pretend you got a new function, which is going to be 2 to the x plus 3. Remember our friend 2 to the x? We already analyzed that earlier. This is not what I would call a pure exponential function. A pure exponential function has a base and an exponent, and that's it. No more. Just a base and an exponent. That's what we would call a proper exponential function. I call it pure. This is unpure because it's just not 2 to the x. It's 2 to the x with something on it. This 3, remember, moves the graph up by 3 units. Now we know 2 to the x. 2 to the x is back here. There's the graph. The horizontal asymptote is 0. It goes through 0, 1, 1, 2. But now we're going to shift the whole graph by 3 units. So there is the x-axis. The asymptote, the horizontal asymptote now is at 3 because we moved the graph by 3 units, up by 3 units. The graph is going to go like that, a sketch. This point is not going to be 0, 1 any longer. It will be 0, 4 because it was 0, 1 earlier when we didn't have the plus 3. And now it's going to be 3 more than that, 0, 4. Remember the point 1, 2 that used to be there on just 2 to the x? Well, now it's going to be 2, 5. And remember here we had negative 1, 1/2. Well, now it's going to be negative 1, 3 1/2. Oftentimes, I will rewrite this as 7/2, same thing. But there we have it. Just a quick sketch. We got to know where the asymptote goes, and we got to go where some basic points go after the transformation. Not to confuse that with example 12, f of x. So we have a new f of x, which is going to be 2 to the x plus 3. Big, huge difference. Exponent is x plus 3 versus exponent is x. We are adding 3 after the fact. Big, huge, gigantic difference. If we confuse those two, we are not doing our job. We are missing the boat. Okay, so that means a shift to the left from the original 2 to the x. Remember way back here, example 1, 2 to the x. So now we're going to shift this 3 units to the left. Now, this is an infinite horizontal line. What happens if you shift the line that way 3 units that way? Well, it is still the same line. So the horizontal asymptote is not going to change. It is still going to be y equals 0 because you're pulling it this way, and there's more of it as you pull. You know, they just keep going on and on forever. So you pull it, and it's still the same line. What changes, oops, is that the graph is going to hit the y-axis not at 1, not at 2, not at 4, at 8, because we're shifting this to the left. See, oh, so the graph is 0, 1, the original 2 to the x, 1, 2, 2, 3, 2, 4 rather, 3, 8. When we shift to the left, boy, that's, well, the outputs are getting shifted to the left. So this 8 moves all the way to here, to 0. Yep, so we have 8 here. That's the new y-intercept. 1, 0, which used to be a point, now has become, rather 0, 1, not 1, 0. 0, 1, which used to be a point, now will be negative 3, 1. So there's going to be a point here, which is negative 3, 1. And then we're going to have negative 2, 2. And then the point that had the fraction in it will be negative, negative 4, comma, 1/2. Yeah, practice this. Tons of books have tons of problems on the transformations of exponential functions. Make sure to practice it. 13, and then after that, I'm going to show you one other thing. Yeah, another brief thing. 3 times 2 to the x, which is not the same thing as 2 to the x plus 3 or 2 to the x plus 3. This, remember, stretches the graph in a vertical way. The gaps also get stretched. So let's go back to 2 to the x. Here it is. So everything gets stretched away from 0, or away from the x-axis. It gets stretched. But the x-axis doesn't get stretched because it's away from the x-axis. And I mean, it's in the middle. The x-axis is in the middle of the stretch. So that doesn't get stretched, doesn't get moved. The horizontal asymptote stays there. The rest of the graph gets stretched by a factor of 3. So the asymptote is still going to be y equals 0, and the whole graph gets larger. So remember, we used to say that the graph goes through 0, 1. Well, no. This time it is going to go through 0, 3. But this is not what I would call a pure exponential function. It is affected by 3. So, and then remember we had 1, 2 as one of the points. No, now we have 1, 6. And over here, instead of having negative 1, 1/2, now we have negative 1, 3/2, because the 1/2 gets to be multiplied by 3. Practice this. And I want to close this video with one other thing. I guess we'll label this at example 14. If you're given this problem, solve 2 to the x equals 0. There is no answer. There's no solution. We may never, ever, ever get to an answer. If you have a pure exponential function equal to 0, that is nonsense. It will never happen. So if we say solve this, period, we can say, nope, there is no solution. We cannot solve that. And the reason is, well, the asymptote is y equals 0. In this case, the graph gets on this end closer and closer and closer to 0 without ever getting to 0. So we will never, ever, 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 never, ever reach 0. Never. If we have a pure exponential function. And you may be thinking, hey, how about the other one? Hey, that's just a flip. It will never be 0 either. So watch out. If we give a problem, I guess let's do a problem. 15. If we give this problem, x minus 17 times 2 to the x equal to 0. So we can use the product principle property. We have a product of two things equaling 0. On one hand, x minus 17 is 0. On the other hand, 2 to the x equals 0. This has no solution, but that doesn't mean that the whole problem has no solution. This does have a solution, which is, of course, 17. That is the only solution. Only solution. Eventually, we're going to do a video about equations, solving equations. Right now, we don't. This is not the focus of this video, but I wanted to give you a little preview of one of the things that is coming. And 2 to the x has never, ever, not even, I have to think about a complex number, but I don't know if a complex number will, I have to think about that. But in general, we say, no, there is no solution at all. Okay, we're going to stop the video here.